FDA Center of Devices and Radiological Health. I'm in the research arm of the center, specifically in the division of imaging, diagnostics, and software reliability. My work is mainly focused on using my expertise to support the medical imaging evaluation, devices evaluation, and the related algorithm evaluation. Today, I'm going to talk about the R data package of multi-reader, multi-case studies, and simulation tools to support the development of reader performance evaluation methods. This work is collaborated with Qigong and Dr. Brandon Gallas. Here is my today's outline. I will first introduce what is multi-reader, multi-case MRMC study and MRMC analysis. The ROC receiver operating characteristic curves is one of the analysis methods that can be used to analyze the data generated from the MRMC study. Then I will introduce what is R data package and how we can create one. Based on the R data package, I will show some examples of the MRMC data analysis. By giving this talk, we would like to examine our research data, method, and tools. We would also like to enable other investigators to develop methods and tools in this area. When a new medical imaging devices come to the market, we want to assess its performance, especially compare it with the traditional ones. In the field of radiology, right now, the new technology has made it feasible for the clinicians to read the digital image instead of reviewing the conventional films. So to assess its performance, we want to ask the question whether the clinicians can review and interpret the digital image as well as the conventional films. In another scenario, we have more and more computer-aided diagnostic devices and algorithms. So here is an example showing the AI algorithms can detect the potential lesion position before the clinicians make their diagnosis. So we want to ask the question whether this kind of computer-aided diagnostic device or algorithms can truly improve the performance of the clinicians. In both scenarios, we want to compare the two modalities for a specific medical task. To design a study for this, we want to ask the clinicians to review several cases under the two different modalities. So in this study, we have three factors: the clinicians, cases, and modalities. To compare the difference caused by different modalities, we want to have the clinicians and cases as random factors. That is, to randomly select cases from the intended case population and to randomly select samples from the intended reader population. That is what we call the MRMC, multi-reader, multi-case study. So in this study, each case is reviewed by multiple readers and each reader reviews multiple cases. By doing this kind of MRMC analysis, we account for both the case and reader variability so that we can generalize the result to the population of the readers and cases. This kind of studies can be applied to more than the comparing medical scores from clinicians, but comparing the machine learning algorithm result with the medical scores or comparing the result from different machine learning algorithms. It can also be applied to other areas that have a specific classification task, such as the fraud detection or back screening. In the classification task, we have some positive cases and some negative ones. A reader will give their confidence score for each case based on their experience. If the score ranges from 0 to 100, a score close to 0 means the reader is very confident that the case is a negative one. If the score is close to 100, it means the reader is very confident that the case is a positive one. If it's in the middle, it means the reader is not sure whether the case is a positive or a negative one. So in the MRMC case, we have multiple readers review the same cases under different modalities. So here is what the data looks like for an MRMC study. The first three columns are the three factors in our study, the reader, case, and modality. And we have the scores for each combination of those three factors. Usually, we also have the ground truth for each cases. To analyze this kind of data, there are many ways. One way is to do the binary performance analysis, that is called compute the sensitivity and specificity for this. Another way is to do the ROC, the receiver operating characteristic analysis. To draw an ROC curve, we first need to order all the scores from the reader. To set each score at the threshold, the case with the score greater than the threshold will be predicted as positive, and the other case will be predicted as negative. Then we have this conversion matrix, and we can compute the sensitivity and specificity for each threshold, which corresponding to 1 point on the plot. As we move in the thresholds to the left, we can draw all those points. The line that connects all those points is called ROC curve, and the area under this ROC curve is what we call AUC, which represents the probability that a random positive case has a score greater than that for a random negative case. So if a reader has a high AUC value, it means it can separate the positive cases from the negative ones very well. For multiple readers, we will use the reader average AUC to limit the effect caused by the reader variability. And to compare among different modalities, the primary endpoint would be the difference of reader average AUC among those different modalities. And to estimate the uncertainty of this primary endpoint, we want to calculate the variance of difference of reader average AUC, which is very hard because we have very complicated correlation structures caused by the reader reads different cases, or the same case is revealed by different readers. As we've seen the data structure before, we want to collect the confidence scores from each readers for each case and each modality. So usually this kind of multi-reader, multi-case study is time-consuming and labor-intensive. And right now, not much data is publicly available. So we want to use the R data package to store and distribute our MRMC study data. To deal with the complicated correlation structures, we have another R package to do the MRMC performance analysis. Let's first look at the R data package. It has many benefits. The first one is to store and distribute data along with its documentation. It has very well organized documentation. It has the descriptions for the overall data package and the format and source for each specific dataset. This package can be uploaded to CRAN, the Comprehensive Archive Network, and can also be uploaded to GitHub to be distributed. The data package can provide use case for future method development and for help sizing the future studies. To build an R data package, we use the GASP2s, which is a development tool for R package development. The basic package skeleton looks like this. In the description, we can edit the entries for the information of the package. The use data raw function is specifically for the R data package. So we can have this data raw directory to put our raw data in it. And in this folder, there's another R file where we can put data preprocessing script there. And by calling the use data function in this file, we can save the R formatted data into data directory. Here is an example showing how we use the R data package to store our MRMC data. In the color scale study, we asked the clinicians to review CT or MRI image and the different color scales like grayscale, rainbow, and hot iron to see whether there is difference among different color scales. In the data package, there are two files to give the general information of the overall study design and the package. So the description file is for the R package and the README file is for the GitHub. In this study, we have two sub-studies. One is for CT image and the other one is for MRI image. So in the data row, we have 4 CSV files. For each sub-studies, we have one file for the ground truth and the other one for reader study data. And the 4 R files reads in each of those CSV files and output the R formatted data. This data can be easily accessed in R. We just need to load the package. So in the backend, the data is already there. To document each specific data set, we can edit the data.R files to give the title, description, format, and reference for each specific data set. By calling the document functions in DevTools, it can generate this .rd menus automatically. And in the RStudio, we can find these files as the help page for each specific data set. To build the package, there are two ways. One is to use the build function in DevTools. Another way is very convenient, is just click the build and reload button in the RStudio. So far, I have talked about the structure, documentation, and how to create the MRMC R to the package. The next part will be how we apply the MRMC analysis on this data package. I will show the functions in the IMRMC package. So IMRMC package is a standalone pre-compiled Java application developed by Dr. Brandon Gallas' lab. It is used to analyze and size MRMC studies and use the statistics estimation for the variance of difference of reader average AUC. It contains an R package, the IMRMC R package, which utilizes the core Java application and output R list object that contains all the results. There are two core functions in the package. One is to use the ROC data as data frame and runs the MRMC analysis based on use statistics. The other one provides a simulation tools to simulate the data and allow testing other new methods. I will show an example of how we can use the dual IMRMC function to our color scale study data. We'll focus on the first sub-study, the CT image study, in which we involve 12 readers and 210 cases. The images are in 3 color scales, the grayscale, rainbow, and hot iron. To apply the dual IMRMC function, we need to combine the ground truth and reader study data into a single data frame. And then by calling this function, we can extract the AUC and variance of AUC for each modality by use statistics method from the result list. And we can also get the difference of AUC and variance of difference of AUC for pairwise comparison among different modalities. So we can see here are the grayscale versus hot iron, grayscale versus rainbow, and hot iron versus rainbow. Based on this result, we can construct the 95% confidence interval for the difference of AUC. Since all the confidence intervals contain 0, it means there's no significant difference among those color scales. For more information about the use of function and data, we have the R Markdown files in the package. And we have another R data package called Viper that is also publicly available. To simulate an MRMC dataset, we usually use the raw mass model, which involves 4 factors: the modality, reader, case, and choose state. The modality and choose states are fixed factors reader and cases are random factors. To simulate the data, we first need to set the size of the study, the mean and variance of each component in the models. And then we can get this kind of MRMC data. The first part is the ground truth, and second part is the reader study result. From this simulated data, we can draw the distribution of the reading scores from all the readers for each modality and each truth state. By applying the dual IMRMC function to our simulated data, we can get this reader average ROC curves and compute the AUC for each modality. So in summary, today I'm mainly talking about the multi-reader, multi-case MRMC studies. We use the R data package to store and distribute our data. We use the IMRMC package to do the MRMC ROC analysis and provide simulation tools to facilitate further development of methods. Here are some links. Thank you.
No questions? Okay. Last call. Okay. Start of the session. We have to identify. My name is Mike Bell. Our second speaker is Andrea, and she will be speaking on hierarchical models and production of vision statistics, a discussion of some practical aspects.
Thank you.
Sorry, go ahead.
Oh, is this one? It was open. You just closed it. No problem. You just. Right. Can you see it? Perfect. Okay. Okay. See. Okay, works. Okay. Thank you all for being here. As Mike said, I'm Andrea Erculescu. I work at WestTech, and I will talk about hierarchical models in the production of official statistics. And particularly, I'll try to touch on a few practical aspects. So why hierarchical models in the production of official statistics to begin with? And I think that the hierarchical models framework can help with three major needs that we have in producing official statistics. And those are listed here. So for example, accounting for values of error, sampling error, measurement error, linking error, and also in a transparent, reproducible, and validated process, and also with the need of measures for uncertainty, because we can get more than just point estimates, for example, the variance estimate for certain quantities of interest. So a general framework for a hierarchical model is listed here. So say we have data Y, so we assume a data model Y given theta and psi, but the quantity of interest is really theta, and psi is just the vector parameters. And then we assign a process model on theta, so that theta given psi, and finally a parameter model on psi. We can write the distribution as the part of the tree. However, as I said, interest is in theta, so that's the quantity of interest. So we have to derive the predictive distribution, and that's theta given y and psi. And there are three cases that we can talk about: known psi, which is not common in practice, and unknown psi, either fixed or random. Now, as you probably mentioned in the abstract, I will talk about small area estimation. So how do these two, what do they have in common? Well, I small area estimation, in particular model-based small area estimation, also helps in the first three images. And on top of that, we can also integrate data from multiple sources. So we can integrate observed survey data with auxiliary data, and information. We can use information across all the areas in the sense of small area estimation. And also, it helps with the statistics. So, for example, quantity of interest as total, means, and ratios are of interest for very fine domains, and those areas or domains may be defined not just in terms of geography, but also in terms of socioeconomic status or occupation. And I will give a few examples in the next slide. And finally, it helps with the increasing cost for data collection. So what do I mean by small as a small area? Well, it's a domain or an area where the survey data that's available for that, it's very small. So it's not sufficient to produce reliable estimates. And the sample size may be as small as 0. So building on the hierarchical model framework that I just showed, a small domain hierarchical model may be within the same form. So the first data model here are replaced by the sampling model because really the data that is available, say yi, where I it's derived using the survey data. So that's the sampling model. So we have yi for single distribution y given data I, maybe some covariance available xi, and I use here just as a parameter site data. And the process model for data is really right now a linking model because we're linking the quantity of interest data I with some covariance xi, those are available. And finally, the parameter model for the parameters. Now, again, we have to derive the predicted distribution theta I given yi, xi, and the parameters in order to make inference for theta. Typically, in an area level model where yi and psi yi are available for domain I, those are typically assumed to be known. So they're available. We derive them using survey data. And again, on site data, we can talk about 3 different cases: known, which is not common in practice, or unknown, experiment. So I would like to give some examples of model-based small area estimation approaches that have been already considered or implemented in some government programs. So for example, the Chilean Ministerio de Desarrollo and World Bank are using small area models to construct poverty mapping estimates. At the Census Bureau, a small area estimation model has been used for income and poverty measures. The National Agricultural Statistics Service, we've been considering small area estimation for 3 different programs: cash rental rates, cross production, and agricultural labor wages. OECD, in collaboration with NCES, particularly has been interested in adult competency rates. So for that, we're also looking into small area model-based approaches. And finally, at Bureau of Labor Statistics, concurrently, I'm working on a small area estimation model-based approach for employee compensation components. So this final one I'm going to use in this talk as an example, just to show you what I mean by that specifically. So for example, here, this is a hierarchical-based multivariate model for employee compensation components. So again, the sampling model assumes for yi given data I, and here yi is a bivariate vector. So I have survey estimates for domain I for both wage and benefits, the 2 components of employee compensation. And I here denotes the domain, and in particular for this application, the domain is defined using a cross-tabulation of census divisions, so that's groups of states across the US, 6 digits SOC system codes that denotes the occupations, work levels within the SOCs, those usually range from 1 to 16, and some other binary characteristics that characterize the jobs, for example, full-time or part-time or time incentive. And again, the quantity of interest is theta I, so I'm assuming a linking model for theta I given data in sigma v, so a matrix, variance covariance matrix for the linking model. And I'm linking here theta I with some covariance xi. For this particular application, auxiliary data was not available, so I constructed covariance using also the survey data. I'm not going to go into those details, but this is just to give you an example of how this framework can be used. And finally, for the parameters beta and sigma v, I'm assuming independent priors. And this model was presented at JSM. So what is a common approach for fitting and prediction for hierarchical models? And in particular, right now, I'm looking at small area estimation using the framework, a hierarchical model framework. One approach would be a Bayesian approach, so we can fit these models using MCMC. So for example, we can conduct multiple chains, large number of iterations, forwarding the first few, and maybe do some cleaning to keep as independent as possible samples for inference. So suppose we keep R samples for inference in total. Then how can we construct prediction? Well, in particular for the small area setting, we can talk about prediction for domains where survey data was available. So I'm gonna call those in-sample domains. So using the R samples that we have available for data I, we can construct posterior summaries, for example. And the second type of prediction that I can talk about is not in-sample prediction. So that's for domains where survey data was not available. I can still use the model, and I can still predict for those domains. So in that case, I need to generate R samples, and I call them theta I times data from that predictive distribution, and then again construct posterior summaries. What are some practical challenges that we need to take into account here? So we need to be aware of the number of MCMC samples. In general, the more iterations we use, the better. But we have to conduct model validation at the end to see what is best there. So I want to make sure that I recognize the practical challenge that relates to time. So this model, the more complicated they are, the more time consuming they are. And for particular for the employee compensation example that I gave, I'm working with a very large number of domains. For that one, for example, I have 16,000 in-sample domains and more than 500,000 not in-sample domains. So constructive predictions for that large number of domains is again computationally intensive. And finally, variable selection. So again, if we use covariates for that linking model XI, then we have to use variable selection techniques. The more variables we have to select some, and it can get very complicated. Another benefit of hierarchical models would be prediction for other functions. So building on this setup that I just showed you, one can construct predictions not just for theta I, but also for some functions of theta I. Say, for example, you instead of, well, I was modeling wages and benefits for that particular example. Say someone is interested in the employee compensation. That's the sum of wages and benefits. So we can just sum the two components of theta I. And again, we have a large number of iterates that we kept after fitting the model. So we can construct inference for that theta I. Another example would be from the OECD study that I mentioned on adult literacy. There we modeled jointly proportions of adult literacy or numeracy scores in pre-specified ranges, but then we can also draw inference on the sum of those two. Another example would be a ratio of theta I components. For example, instead of modeling wages and benefits like I showed you, one can model, say, total income and total hours worked, and the ratio of those two quantities would be of an estimate for wage. So that ratio again can be constructing straightforward weight inference for that ratio can be done. In the agriculture application, one can also model jointly total production and total harvested acres and derive yield estimates, which is the ratio of those two. And finally, it's again straightforward to construct prediction for aggregates of theta I. In the employee compensation example, we were modeling data as 6-digit codes. Those are nested within 2-digit SLC codes. So we can just simply aggregate those theta I's with 2-digit codes and construct estimates. If you think about a geographical aspect, if you model data at the county level, then again, any other aggregates can be constructed, right? Like agriculture districts or states or sensitive divisions. As with any model-based approach, model validation is critical. So in general, there are internal methods that one can use. For example, to test for mixing and convergence if you use MCMC with multiple chains. And I just listed here some tests for that. Residual diagnostics to check some of the model assumptions that were made at both level, sampling level, and linking level. posterior predictive checks, and some other alternative model specifications. For the small area estimation aspect in particular, we can also conduct external model validation. So we want to compare the model predictions with the direct estimates, or also we can make comparisons of the distributions of predictions for those in sample domains and those not in sample domains. And finally, cross-validation. Again, there are practical challenges associated with this. Autocorrelation tests may not be feasible. For the example that I gave you, the employee compensation, I was not even able to construct some autocorrelation tests because of the dimension of the data. Cross-validation, again, it's computation intensive, and so forth. So I looked into a specific aspect, and I conducted a simulation study. I'm not going to go into the details here, but again, I'm using the hierarchical models, and here yi is bivariate, theta is bivariate. So I generated some data and then fitted a model that's exactly similar. So I'm not testing here the model. I'm rather going to compare two softwares that are already available to fit this kind of models. So that's RSTAN and RTAN. So I also looked at a Bayesian specification again and looked at two different approaches: a hierarchical based approach where priors are assigned for all the parameters, for beta and for sigma v, and an empirical based approach, semi, because I'm fixing most of the beta parameters except for the intercept. All of the other parameters are fixed and set equal to a least squares estimates based on multiple linear regression models fit separately to the two components of y. And only assign priors on the intercept beta and still assigning priors on the sigma v matrix. So sigma v is a 2x2 matrix in this case. So I'm using an inverse Wishart matrix with scale 3 and the matrix, the identity matrix. Now, given these two softwares, there are some practical challenges associated with them, specifically in the adopting priors for the linking model that is matrices. Using our JAGs, one can use conjugate priors, and this is one example, the inverse Wishart. But in RSTAN, RSTAN is more flexible, so I can look into a decomposition of the matrix and assigning priors on standard deviations and a correlation matrix using an MKJ prior. But for this comparison, I want to use the same prior, and again, the only difference here is the two different softwares. So to finalize the specification for the simulation, I'm considering either 100, 1,000, or 10,000 domains. And in terms of parameters, either 10 or 100. So there are three combinations there. So S1 would denote the model that was fit using our STAN. J1 would be the model using our JAGs. And J1L, it's again the same model fitting in JAGs, but with a larger number of iterations. So these are examples of code. I'll be happy to go over them after the talk, but this is an example for the hierarchical-based model specification for the bivariate model in JAGs, and empirical-based model specification again in JAGs, and similarly in STAN. And so finally, some of the results that I was interested in are the computational time. As you can see, the final setup, I was not able to get results in back to the stop. That's too long. But for the rest, I can still compare and notice that, first of all, yes, the empirical-based approach does, it's faster because, again, I'm setting most of the beta parameters as fixed, so I'm only assigning prior on the intercept. So as expected, that takes less time. However, model validations are very important, and I'm going to get into that. And comparing STAN with JAGs, this is a very interesting result because JAGs is much faster. Notice it took 5 seconds to fit the same model versus STAN that took over 500 seconds for this setup, and comparable results for the other two setups. So as I said, it's important to look at some validation results because not even if it's faster, it doesn't mean that the chains conversion mixed properly. So for example, using an R-hat measure and an MC effective sample size measure here, I compared again the different setups, and notice that under an empirical based approach, it takes longer. So for the same number of iterations, the models, the conversion diagnostic don't look as good. So usually this R-hat should be less than 1.1. So notice that it tends to be larger, especially for the EV approach. So that's a different talk. So just an example of output that I can show here. Again, related to the example of employee compensation components, this would be 4 plots of model predictions that were constructed using the bivariate hierarchical model for wages and benefits. So the first column would be wages, the second column is benefits, and the first row are point estimates, the second row are standard errors. But again, we can get the entire distribution. You notice there are 3 curves. In blue are the survey estimates, so those are about 16,000 domains for which we had survey data. In red are in-sample model predictions for the same set of domains. In black are predictions for the not in-sample predictions. So those are more than 500,000 domains for which we generated. The multimodal distribution in black is due to the nature of covariance that we use for this application. But what's important here is that we can compare the range of predictions. Again, we were able to use the model to construct it very way. So some final thoughts. I hope I left you with a flavor of innovation in official statistics programs, as opposed to just using the traditional survey-based estimation approach. One can use right now multiple sources of data, and there are already existing tools, and there's potential for development of novel ones. In this talk, I only looked at RJAX and RSTAN. There are other software one can fit this kind of model, even more complicated. SAS has a PROC MCMC that can be considered. Also in R, there is another package, BRMS, that one can look into. Alternative sampling methods can be also considered. For this simulation, I used the RSTAN, the default sampling method, not the U-turn sampler, but there are others like the Hamiltonian Monte Carlo, or again, another empirical based approach where you can fix some of the parameters. And again, on top of all the challenges that I mentioned on the slides, I want to emphasize time because this is very important. I wish I knew it before I started working on this application, because at the beginning, I started fitting all the models in RSTAN and everything took so long. So then I had to rewrite everything in JAG. So these are some considerations that are good to have in mind before implementing some of the models. I want to let you know that one can go beyond smaller estimation. I chose this example here, but hierarchical model framework can be used for others. And currently, we're working again with an agency, the Association of Fish and Wildlife Agencies, and we're bridging 2 complex surveys. And again, we're building models that are as a hierarchical model. So these are some selected references. Thank you.
Any questions? Question
Yeah.
there. Have you tried? Have you thought about using variational methods instead of MCMC? I think RSTAN also supports that.
I believe that's a great question. I think variation methods are the state of the art methods right now. They fit this kind of models. I think RSTAN already builds of that, so not the user sample, they use some of that. These are very the model here is actually pretty straightforward. I use normal distributions above the sampling model and the linking model, so even MCMC can be avoided here. There are other methods to sample from this model, but I have not looked into the variation method yet. Thank you.
And our third speaker is Benjamin Bloom of the Federal Reserve Board. I know his presentation is how you model risk.
Hi, my name is BJ Bloom. I'm a data scientist at the Federal Reserve Board in the Division of Consumer and Community Affairs. And I'm going to be talking about topic modeling consumer complaints for risk analysis. The standard disclaimer applies. These views are my own and do not represent those of the Federal Reserve Board or the Federal Reserve System. So it's a little intimidating to follow that previous presentation since I'm not giving quite as technical of a talk. I appreciate that there's a variety of technical skills here, and I actually do include a math slide that I normally keep away from people who are terrified of math. So I felt that that was appropriate here. So the basic question here is, how can we understand risk in consumer financial markets, and how can we use consumer complaints as a way of getting at this kind of potential emerging risks in consumer financial markets? So by consumer financial products, I mean consumer loans, mortgages, student loans, auto loans, and then also non-credit products like debt collection, credit reporting. These are things that are regulated in different ways by the CFPB and the Federal Reserve Board, as well as the OCC and the FDIC. And the Fed itself does collect some complaints, but the volume that we get is 20,000 since 2012, as opposed to over, I think now 1.3 million complaints from the CFPB. So, and our data sharing agreement allows us access to the unredacted narratives from the consumer complaints narratives submitted to the CFPB. Those are not publicly available. Some people, you're allowed to opt into sharing your complaint if you submit a complaint to the CFPB. They redact all PII, but only about 30% of those complaints actually make it into the public database. So this broader set of complaint data is what I'm working with. There are some, of course, inherent limitations that I always want to stress to people when you're looking at consumer complaints. First, consumer complaints are not a representative sample of a consumer experience. It takes a lot of effort to actually go through and make a complaint. I do tend to think if one person is complaining about a certain area, that means a few people may not have taken that step, but it's no way representative sample. We have survey data at the Fed that we use to supplement this kind of thing, but this is not a survey. Second, complaints vary in their salience. If you have a late fee that you think you weren't charged with and you call your bank on your credit card and you have someone's rude to you on the phone, that may be annoying. It's not the same as if you're trying to work with your bank on a loss mitigation application and they foreclose on your house. Like, those are very different experiences. That's not captured in the data. That's more of a qualitative measure. Finally, complaints don't necessarily mean a company did anything wrong. The biggest complaint about accounts and services is about overdraft fees. Banks are allowed to charge overdraft fees as long as they follow the CFPB rule on that and implement their own policies and procedures appropriately. So in risk assessment, we look at meaningful trends, not the veracity of each claim. And complaints are only one component of the overall risk analysis that we do. So the CFPB does collect metadata on the complaint. When you submit a complaint, they ask you about what you're complaining about, the company, the product, subproduct. So if there's a mortgage and if it's a standard loan or an FHA loan, and then just the general issue. And there's some limits sort of to what these categories are that they have in the database for you to choose from. First, some categories are quite broad, some are quite narrow. In the credit card product, there are about 100,000 complaints. There are 55 categories you can choose from to qualify your complaint. Of those, 24 had fewer than 1,000 complaints and 14 had fewer than 200. So it's a little hard ahead of time to think of how to create these categories before you start collecting your data. Some categories, for let's say accounts and services, you would have opening, managing, or closing your account, which kind of captures all complaints about your credit or your savings account. And there's some duplicate or ambiguous categories. I think one is a problem caused by my funds being too low versus problem caused by your funds being too low. Just the way they collected these categories and got them ready in time for this database to start collecting them, they may have missed some of those issues. But fundamentally, the way consumers talk about financial products differs from how regulators think about them. And the CFPB did recognize some of these limitations and recategorize their metadata in April of 2017. But that leads to this kind of graph when you look at time series and see if you can tell where the change was made. So the solution that I've come up with is to use a natural language processing technique called topic modeling. And topic modeling, as with all natural language processing, takes unstructured data as text and converts it into data that can be fed into an algorithm to create some sort of result. In this case, it's called latent Dirichlet allocation, which is a Bayesian model which says that given a number of topics, it will iteratively assign words to topics and topics to documents as it updates data in those documents. Here it is formally. I'm not going to go through all of the math, but you have some prior assumptions about the distribution of topics across documents and the distribution about words within each topic. If you don't know anything else, you will set these kind of low so that you assume there's a kind of even distribution across your corpus. And your latent parameters that you're trying to estimate, K you actually tend to set yourself. That's the number of topics. I'll show how I go about trying to find the optimal K value. Theta is a topic distribution in each document. Phi is the word distribution of each topic. And Z is the word topic assignment. So what you're mostly trying to do is find the topic Z given word W. And you then use, as the previous speaker was talking about, the MC chain method. In this case, it's a Gibbs sampling. You start by initializing and using a burn-in method, and then iteratively going through each document. For each word in the document, assign a topic to the current word based on the probability of the topic given a topic of all other words. I don't really want to get into all of the math that goes into this, but and this is the more conceptual process of how this works. You have a set of documents, in this case are complaints. It goes into the model, and what you get as your output is a list of words for each topic, and then a probability distribution of topics for each document. So just a conceptual example, say you were given 5 years worth of newspapers at the Washington Post, but you had no headlines and you wanted to understand what was in these articles. Create a topic model of 3 topics. Your output could be, topic 1, election, poll, moderate, healthcare, rules. Topic 2, goal, score, team, fans, rules. Topic 3, theater, play, drama, fans, rules. Review. So the point here is that one word can appear in more than one topic, but as you look at these word lists, distributions, you get a sense of what the topic is. It allows you to identify topics, to review specific articles containing certain topics, and look at topics and trends over time. So if you had maybe 30 topics, you might be able to separate out hockey articles from baseball articles, and you can see how the seasons, number of articles in that corpus of documents change over time. However, it doesn't replace the actual headline of an article. And I used R for this. There are a couple of packages. I use the text miner package. The biggest challenge here in topic modeling is understanding the quality of the model and selecting the optimal number of topics. The main general NLP packages, TM was the first one that I think some people still use. Tidy text is now the one I think is most widely used. For topic modeling, LDA and topic models were the first 2 ones to use, but there weren't a lot of model diagnostics to tell you about the quality of the topics. Whereas STM, or structural topic model, and text miner both have these types of things. STM is interesting, and I may use again in the future. It allows you to incorporate metadata into the topic probabilities, the prior distributions, which usually you don't have much information on those. If you have some metadata, you can plug that in. Text miner though gives 2 diagnostic measures, an R-squared equivalent and probabilistic coherence that help assess the model. So probabilistic coherence is kind of how coherent is the topic that you are getting out of your model based on the words that are assigned to the topic. So the logic is, if we restrict our search only to documents that contain, say you have a pair of words A and B in topic, the top 2 words in a topic. If we restrict our search only to documents that contain the word A, then the word B should be more probable in those documents than if chosen at random from the corpus. probability of B given A measures how probable B is only in documents containing A. Probability B measures how probable B is in the corpus as a whole. If B is not more probable in documents containing A, then the difference of probability B given A minus B should be close to 0. So this is a measure of how associated they are, controlling for statistical independence. You can do that. That's for 2 words. You can do that up to 5, 6, however many words you want, and then you average that calculation to get a probabilistic coherence measure for that topic, and average it across all topics in that for that given K value, which is the number of topics, to get the average probabilistic coherence across all topics, and then you can get graphs that can kind of tell you what number of topics you should be having. So you want, obviously, wherever the graph goes up, it kind of works, it kind of doesn't. That's the problem. It works when it does. It depends on sort of on the data that you have. Basically, this is telling me just to keep increasing K indefinitely to increase the R-squared value. But in this case, some practical business concerns took precedence over the optimal solution. And what I'm not doing Federal Statistical Agency publishing of public results. I'm not publishing this in a journal, so this is all internal research. I can take a few liberties when it comes to how technically sound all of these things have to be. This is for internal use only. It's an improvement, I think, over what currently exists. It's not going to be perfect. So there are 11 products in consumer finance that we're looking at. One of them in credit reporting, there's a legal reason we can't look at the complaints themselves. So I built 10 models, one for each product, the product specific, but I limited K to at most 40 topics just because I'm going to be sharing this information with people. I'm looking at trends over time. And it's easier to summarize and create trend lines and put this into a dashboard for people if you are not doing 80 topics. And some of these topics, even though the probabilistic coherence measure does tell you it's coherent and distinct and separate from another topic, they can relate to each other when you start looking at them in more depth. Second, topic models usually, the output is actually a distribution of probabilities for multiple topics. If you go back to the Washington Post example, say you had an article about Bryce Harper and you're leading a fundraiser for Muriel Bowser, like it could fall into both the sports category and the politics category. A lot of complaints are going to fall into more than one topic. To avoid double counting and to avoid having my figures look weird, I just take the most probable topic and sort of hard code that document to be that topic. And then there's also some manual review involved in this. I think that's a good practice to help understand your data set anyway. It helps me go from this kind of figure where I have a list of terms. So it does improve your categories. In this specific case, it smooths out that line. You can see mortgage complaints are actually going down, which I assume is a good thing, compared to the last category. And then if you do manual review, the figure on the right, you can actually fill in specifically what these topics are about. The results of these models are incorporated into a broader risk report for key stakeholders and an R-Shiny dashboard. Our team compiles a set of risk reports. The consumer complaints report is just one section. We use both the complaints sent to the Federal Reserve Board and the CFPB for a broad market overview of the consumer risk landscape. So the purpose is to understand emerging risks based on data from multiple sources, market data, supervisory findings, and these complaints. I was going to demo the R-Shiny dashboard. There was a little sensitivities about that. So informally, if you're interested, I could probably show you after the presentation. I have 2 dashboards. I personally like R-Shiny. I like to be able to control everything. There's a lot more customization. And particularly, I don't have to get a DBA involved in creating a view in a database, which you kind of need for Tableau. I think there are ways of getting around that, but I just like working R-Shiny. There is a bit of a learning curve because it's a little different than standard R. So overall, I think this is a good way of identifying particularly emerging issues you might not have thought of ahead of time. for example, there are a lot of fintech products that were not available at the time the CFPB created these issue categories. These categories could stay consistent over time. The purpose is to look at the broad changes in product markets to inform key stakeholders and potential risks. The complaints themselves are the best data we have to capture customer experience by product. We have a survey of household and economic decision making that takes a good survey, broad survey that informs the consumer's experience with their finances. But this is an alternate set of data. It's a good initial indicator for risk for potential consumer harm, and it's real-time data that identifies trends sooner than other data collection methods. I think that's it. And like I assume everyone, I can't actually post my code on GitHub. I have an example of how I do this that follows, that slightly changes one of the vignettes from the top text miner package.
Your question? Nathan? Are there ever any situations where you're finding two topics almost impossible to disentangle? I know at the Department of Agriculture, we've been examining web scraping as a way to build up our list rankings. So you think about the number of chicken farms versus the number of chicken restaurants, and there are farm to table restaurants. So at some point it becomes hard to disentangle those. What steps do you take in building these models to address that issue?
With a lot of NLP stuff, I've found it kind of depends. You have to try a lot of things. There's a lot of pre-processing that goes on. Stemming out words is one thing, but not just that. There's sometimes you have to make specific customized dictionaries almost that for me, for bank names, I try to keep bank names in because I think they're actual informative, even if they show up as one of the words in the topic model. I think it's an informative way of understanding what's in that topic. For me, it comes down to manual review. It may relate to the number of topics because I have, in reviewing them, said, oh, well, those two things are clearly almost exactly the same, but it's hard to see that in just model diagnostics.
A question over here.
I thought the word choice might be very similar over time, but there seemed to be volatility on your charts. Have you gotten to a meaningful change over time? With volatility.
That is kind of a lot of what we're trying to look at here is looking for these types of spikes and trends. So trends, broader market trends, you'll see sort of increasing, but the goal generally is to look at just market trends, but you can see specific companies that have problems. I can tell you Coinbase, I don't know if anyone is familiar with that. It's this cryptocurrency exchange. Their system went down for a couple of weeks in last year. And you see this just massive spike. And like, I transferred $20,000 into my crypto, Coinbase, and I had never got an email confirming it. I have no idea where the money went. Some people use direct debit on prepaid cards. If you don't have a bank account, this is the way your employer can still pay you. When those systems go down, similar, you see these massive spikes. And you can kind of see that in the categories that the CFPB has, but they're not specific enough to really get at that until the topics can kind of very clearly see that.
Any further questions?
Would kind of an emerging topic be something that didn't show up in the future, or are you thinking about that topic that always existed?
Yeah.
Models.
Mm-hmm. couldn't capture a lot of the most common topics across products like overdraft fees. There's one unfortunate one that always shows up, which is it comes down to basically I lost my job or my wife got cancer or all this. Yeah, everything is just going at once, and I can't afford my mortgage payment. But one challenge I have right now is to identify these emerging issues. The topic model is, if I'm going to update this next year, I'm going to get new topics essentially. And they're going to relate somewhat to the ones I currently have. They're not going to be exactly the same. There are advantages to doing that. I had tried this year, so this is the second iteration, to try to build a predictive model off of the topic labels that I had last year. I found that it didn't work that well. I guess I didn't estimate or understand if I have a data set with 100,000 complaints and 20 topics, it's hard to find a classifier that can classify 20 topics when there's like variation in how many are in each topic. You can do one-off, so you make it a binary problem, but even then you probably only take the ones that have the most. There's a class imbalance issue, so it became complicated and just kind of didn't work. So I'm taking the view that I may get slightly different topics next year, but that's okay because it could identify these new emerging risks. Is that answering your question? A little bit, okay. We'll talk offline because I work with Mike. So.
Any other questions? So about the trends over time, I mean, like mortgage is one of your examples, and maybe economy's doing well, mortgage complaints are going through. The economy is bad, maybe not as many people are buying homes and not getting mortgages, but payday lending shoots up. Is that the kind of thing you guys are kind of look for?
Yeah. Yeah, that's exactly the kind of thing we're trying to look for. We see that kind of information more in market data. One of my coworkers looks more at market data in terms of number of loans by credit tiers. So you can get a sense of, for someone with a credit score below X, the sort of subprime market, we can see payday lending going up, and that does relate indirectly to the economy. There's not going to be a perfect match, but we try to think about that initial. So we divided sort of access, like do you have credit access to loans that you want versus sort of the experience once you have the loan of trying to pay it off, dealing with loan servicers. I think there's not a direct way to say that the economy is doing well, therefore we expect this, but it is to just see what kind of risks there are based on the current economic conditions. And we retroactively sort of see problems that were happening during the crisis.
Any other questions? Okay. Our final speaker this morning is Dylan Holt of Ascension. And this topic is beyond the analysis, approach to operation where so is the open source JavaScript.
Yeah. Okay. I got it on here. And let me see. I'll let you know if it doesn't.
Going to get that out of the way. Giving away some secrets. All right. So good morning, everyone. I didn't know if I should say good morning or good afternoon. So my name is Dylan Holt, and I am an analytics developer at Accenture. And I always kind of have this struggle on how do I kind of define what my role is day to day. Because depending upon the day or depending upon the project or what have you, I might serve as the role of a data scientist. I might be a business analyst trying to make sense of some very quick outcome that we need to get to. I also might be a web developer, depending upon what the need is, or a data engineer. So I kind of try to roll all these up into one term that may or may not actually be a job and call it an analytics developer. So if you're also struggling with what you want to call yourself because you do so many different things, wear so many different hats, make it up. That's what I did. But really what I mean from this is, at the end of the day, I build stuff. I build stuff that integrates data science outcomes into business tools that can be used by a wide variety of audiences. And I also recognize that probably this talk specifically is going to be a bit of a departure from a lot of the talks you might have heard already this morning, in that I won't be showing a model. I won't be demonstrating some analysis that I've done, or even going through. There will be no math on any of these slides, to my knowledge at least. I mean, I built them, but maybe there's something there that I didn't see. But really what this is going to be about is going beyond the analysis, and how do you actually take that model or that descriptive analysis or that task that you worked so hard on to derive some sort of results, derive some sort of outcomes that you believe to be meaningful. How do you in turn make those useful to a broader audience? How do you actually operationalize your results? And I'll be demonstrating this using open source JavaScript framework. And also when I say demonstrating this, I did have a demo, and I have a demo on my computer. I think that's a common kind of thing across many of the presentations today. Is we all have demos on our computers, but we weren't aware that you won't be able to share them here. So this might actually take the form of more of what a lightning talk will be. I might actually breeze through a lot of this. And I would love to do that in order to reserve some time at the end for folks who are interested to come up and actually see the demo that I put together. So with this, one of the key issues that I face day to day in my job in data science is really that last mile. How do you move from an analysis or findings to a production grade, user-centric application? And this can be, think about if your outcome of your analysis is actually publishing. We just had a talk on publishing official statistics. So you've gone through all the trouble of building that analysis to actually publish those official statistics, but how do you make that useful to someone else? Usually, especially in the federal space, that is through a website. And I'll be making a case later as a web as the primary platform for communicating our results. And by nature of that, JavaScript being a great way to do that. Or maybe you have a predictive model that you've built. How do you go that last mile from taking it as a predictive model and making it into a predictive tool? And lastly, does your analysis require feedback from others? Maybe this is more formal and peer review, and you actually want to understand what people are seeing. If they're understanding what your results are, how can you use something like JavaScript and web development to actually facilitate that feedback loop to you? Or maybe you actually did build a machine learning product, and it's important to constantly be receiving new data into your model, or even using other individuals to help kind of validate the outcome of your model. And how might you go about using something like the web to do that? So in doing this, I wanted to present a quick, that's much louder, present a quick framework that you can use to actually go through this process. And there's really three key components I just wanted to quickly go through. And this is, I will admit, this is more of a UI, user interface or user experience kind of talk. But being in the field that I am and sort of in the interlays where I work between data scientists and actually building things for business outcomes, this is really my day-to-day world. And before I even go through this example, this is kind of a bit of an anecdote on why I found this to be such an important thing and really how it's become my day-to-day job. Is I and a colleague of mine were actually on a project where we were building a proof of concept to actually operationalize the outcomes of an image recognition model. So we had our model team, we had our data engineering team, and then we had myself and my colleague who were the front-end developers. Also, both of us being data scientists, but we needed to know kind of what the outputs of those models were going to be. And we were on a call with all these different people on our team. And we're sitting on the call, and they're going through a lot more of like, okay, here's kind of some of the problems we're having with actually appropriately labeling the different aspects of this data so that we have the appropriate information to build and validate an actual usable image recognition model. However, they knew from the whole proof of concept that we would actually be building that into some sort of application. So me and my colleague were kind of sitting quiet on the phone, and we hear that someone say like, okay, well, how are we going to actually get those outputs someone else. And the one leading the model team is like, simply said, that's someone else's problem. He didn't realize that someone else was sitting on the phone. I don't even think he realized that we were on the phone or that we would actually be the ones dealing with the quote problem. So I pinged my colleague kind of, on the side, we're having a sidebar. I was like, I don't think he realizes that we're those people. And it clicked to me that there needs to be a clearer, more, rather a clearer framework on how we actually communicate across teams, be it the data science team, the data engineering team, or the front-end development and application teams. And kind of out came this presentation. I kind of realized that's a little bit of what I do day to day, is actually trying to get people to think end to end. If you know you're building a model, how do you actually think about who's going to be using it, how it's going to be used, and why it would be used? And also understand that this might not be clearly always the case. Sometimes in our work, we're simply just exploring a problem to understand the problem. But at the end of the day, at some point, the understandings that we get from that problem are likely going to be operationalized into something. And going through this framework, how do we actually go from that useful information that we get from our work to actually utilizing that insight in some meaningful way? The first is knowing the problem. That's what we're good at. We know the problem inside and out. But how do we think about knowing the problem in the eyes of a final outcome? So the first question we have to ask, just as I mentioned, is my analysis intended to be applied? Again, maybe it's basic research. Maybe it's just something I'm trying to do to understand a problem. But then after we decide, okay, it is applied. I do want people at the end of the day to be able to use it. So are my features, quote, available in the real world? And I get that it's like, people might have a problem with that. It's like, of course they're available in the real world. Why would I do an analysis on something that's not done? But what I mean by this is like, are they easily reproducible in a real world sense? If it's an active predictive model that's pulling from some sort of data sources, you have to kind of think about that from a data engineering perspective. Is all of the data that you use to build that model going to be available to an external user? And in the case of the government, a lot of times it's not. So how do we kind of keep that in mind when we're actually building different features in our models, as well as building different models for different use cases? And then we might want to ask, would feedback be helpful to my analysis? Not only in the concept of actual feedback like peer review, but feedback in the sense on, did my model get the problem right or wrong? We actually see this a lot in the commercial space. I mean, just think about any product you use in Google. There's now always, I mean, I got it on the way here when I was taking the metros, they're asking me, was the metro full? Did the metro have, like, was it crowded? And that's a subtle way of them actually eliciting feedback from me that's going to turn around and feedback into their models to actually more optimize how they're actually doing recommendations for how you should get from point A to point B. So that's the feedback loop that I'm talking about. So they know the problem there. The second is like understanding the user. So kind of skip over to the right side here. And we have to ask ourselves this question from the beginning: who would find my analysis useful? Kind of noting our audience might know exactly how we want to describe the problem they're in. Or maybe if we're actually, and this was a case for me in one of my projects, deciding between two models that have the similar predictive accuracy, we actually went for the one that had a slight bit lower because it was easier to interpret. It was easier to explain. And that's becoming a much more of a problem at the center of all of this, is being able to explain our outcomes in a meaningful and succinct way. So again, even in a project that I was just on, we chose the model that had a slight less accuracy because it was much easier to explain to our end product users so that they could actually not only use the outcomes of the models, but explain why those outcomes were having, this was in the case of fraud analytics, people were getting more or less flagged for some sort of fraud. And not only do they need to know, like, why am I getting, like, why are you saying I just did something fraudulent? We need to show them the underlying features that went into that so that there was a data transparency there. And then how would someone use my analysis? That goes back in. Is it going to be some sort of tool? Is it going to be some sort of interactive dashboard? How would they want to go through consuming the outcome of something that I'm building? And then lastly, can someone provide feedback to my analysis? So all this kind of knowing the problem, again, what we're really good at, and understanding the user, I think sometimes myself included, although we failed to maybe realize who that might be. Once we kind of have these questions more or less laid out, how do we actually bring that together in a connected product? And in that case, I want to make the case for the web. So the web, I think now is becoming more and more of a useful platform for data scientists to interact with their consumers, of their data, the consumers of their analysis, as well as an interesting sort of bridge now, kind of through through advances in JavaScript, for data scientists to rather become hybrid web developers, if that's something you're interested in, or to interact with web teams. How do you actually start having that conversation? And really, it's because in a lot of ways, JavaScript is probably more than you think it is. Historically, JavaScript is how I would say the muscle of a web page. If HTML and CSS are how a page is structured and looks from a style perspective, JavaScript has historically been the muscle behind that. It's the one that gives us those interactive web pages that we're used to seeing. But over the last decade, we actually have seen quite a change in how people are approaching and using JavaScript. And also realize I might be a little bit outnumbered here too. It's like coming into an R and Python conference as a JavaScript developer. My background is more in SAS when it comes to the statistical analysis side of things. But I realize that also puts me in a unique position to kind of speak to how you would use JavaScript to productionize and operationalize data science models. So again, JavaScript, more than you think. There's been great advances in user interfaces. So there's several front-end frameworks that can be used to expedite UI development. What does that mean? It means you can very quickly get from 0 to something very useful in terms of a user interface within kind of a matter of hours. Using something like Angular by Google or React by Facebook, Vue, there's so many that I can name. And these are all open source and freely available to developers. Another one is visualization. So charting libraries have really grown exponentially in JavaScript lately, and they provide these incredible ways of having a canvas-like approach to, quote, drawing with your data to really allow for these interesting and unique data viz capabilities that you've probably seen a lot more prominently in media outsources like New York Times. And these specifically are more in D3 or Chart.js or plenty of other libraries. And then lastly, and this might not be one that folks are too familiar with, maybe they're familiar with the Python implementations of these libraries, but machine learning can now be done in a browser. It can crash your computer at the same time, but like it can be done. So that's more of an infrastructure talk that we can talk about afterwards. But in this case, especially in the last couple of years, TensorFlow especially has come out with TensorFlow JavaScript, where you can not only build and train new models in the browser, but probably I think more importantly in the case of this talk, you're actually able to take a pre-built model and load it through JavaScript alone. There's no need to hook up to a Python server or anything like that. You can actually go straight in using JavaScript, as well as other libraries like ML5. And I will just say like a little asterisk on TensorFlow is if you built maybe you're more familiar with just kind of building a predictive model in scikit-learn. Scikit-learn estimators can be transformed into TensorFlow models and therefore fit into this pipeline. So if you're doing something in scikit-learn, you can use the same workflow to actually add your model right into your web page for actually running inference on things that the users might want them to do. So with that in mind, I'll quickly just kind of go through some of these slides. So let's assume and this would have been the precursor to the demo I would have shown, but I do have some slides that's kind of demonstrating what that, or just screenshots rather of what that application did. So let's assume you just built an image classifier, and specifically you want to use this image classifier to build captions for those images more automatically. But what now? So again, we have to kind of go through these problems of how do we know the problem? Do we understand the underlying features of what output we're interested in? Do we understand the user in such a way that we know how they would want to consume that information? And can we do that in a certain way to like actually connect the full product? And this example that I'll show in some screenshots and we'll have up here for to play with afterwards was built with Angular as the primary JavaScript framework, D3 as the main visualization library, and TensorFlow to load and actually use a pre-built image class or multi-classification image recognition model. You might be familiar, I'm not sure if you're familiar, but it's MobileNet, which is just a popular image classification model that's actually used a lot for transfer learning, and that's a whole other talk. But we'll just kind of quickly go through the slides of what that demo looks like. So this is just loading the app itself. So first we got to know the problem. So here's an image of something. And our problem is we need to take the features of this image. In the case of image classification, it's the pixels of it, the vectorized set of pixels for this image. And we need to come out with some sort of set of possibilities of what this image is. So understanding the user, maybe the first thing that we want to do is to kind of show them very quickly, what do we think is this image? So the outcome of a model, and this is super quick, this app actually allows you to actually, it gets most of it right. There's some wonderful examples if you want to play with it later that they don't get right. So we have this image, we're able to actually upload it, and that's our problem, it's image. Well, that's the target of our problem. The problem is, what is the image? Using a pre-built model, again, I didn't actually build the model itself. I used the off-the-shelf pre-built model available in TensorFlow. Very quickly, in a few lines of code, upload it or implement it into my web application. So actually, to do that, I would upload this image. I would click this button over here to see what the model thinks it is. And then it runs that image very quickly through the model, tells me the top 10 things it thinks it is. But that still might not be there. Remember, our problem was to create captions. So that's not really a great caption, it's this bar chart. How do we actually go from there in another way and very quickly connect the product? So again, we had the image, the problem to be identified. And then how do we actually connect it in the end by making a caption? By running it through a model, we can actually then just use very simple string concatenation, as well as like potentially even more advanced NLP capabilities to actually build more variety of captions. But here, a simple caption for this is like, it's most likely a tusker, but it could be an African elephant. So I know that was probably just a lot to kind of dump, but all this right here is completely done fully in JavaScript. There's no porting over of Python. There's no need to rewrite something in XYZ. If you already have a model built, you can deploy and implement it today in JavaScript in a useful way to connect to your users. So yeah, if you're interested afterwards, we can have some questions. I know we're kind of nearing time for the lightning talks, but I'm also going to be up here with my computer if you actually want to play through actually some other examples of what this thing can classify. So with that, thank you.
Any questions for us?
Okay, man, almost made it, man. It's fine.
I know you mentioned JavaScript libraries you use. How much do you use also done like table? I don't know JavaScript much. But, you only need to know that anything I should learn JavaScript, you don't use it on Python.
Yeah. Like, should you become a JavaScript developer in addition to all the things you're trying to probably become knowledgeable? Right.
Okay, so the question was sort of how much as a good summary of the question, how much more benefit would you receive by doing something in JavaScript versus just doing it in like Kotlin or you do a lot with Python. Again, there's ways to implement those, and I know that like Tiny is the way you guys develop an app with R. You can how do you interact with web hooks? You can web hooks with Python as well as Python itself has frameworks for web development. I would say those are great. I always recommend using them. I think what I'm trying to demonstrate here is that maybe it's not the case that you go out and become a JavaScript programmer, but rather you have this framework by which you can like think about your problem and collaborate on development. I think the advances in JavaScript. Now, I love JavaScript. It's my language that I use, but at the same time, I understand there's a learning curve there. And then there's an individual learning curve people collaborate might have to learn as well. The thing that I'm trying to say is that if you are a Python programmer and you have built certain things like or TensorFlow, there's no JavaScript capabilities for actually porting that over in a much more seamless fashion. You know, maybe a few years ago, where you would have to kind of custom build some sort of messaging between a Python server and where you're with. So I think there's only value when
really more. I mean, I don't think it's definitely a learning curve there. Rather, I would say use this framework to bring your problems that you can collaborate with web developers. Web developers are really good at this kind of stuff. They know that. And how you actually use this framework to communicate and kind of avoid that problem with colleagues.
Other questions? Okay.
Here's the colleague. So,
So to actually build an image classifier in JavaScript or use image classifier in JavaScript, what are the resources that we're
specifically the one that I use to build, I would say I'm a big fan of TensorFlow, but there's also other JavaScript libraries like ML5, and there's a few more that I meant to mention more on, but TensorFlow is the one I'm most familiar with, and thankfully their documentation is actually really, really good. And they also have quite a bit of tutorials on how you actually go and build these things specifically in JavaScript. Rather, if you're trying to build and train a completely new model using JavaScript fully, a lot more use cases there is if you're actually wanting to use, say, a webcam or some sort of interaction with the computer that you were previously doing with the website. You can actually use that those interactions now, like with the webcam. I think they have one on a actually body positioning that they can recognize if you have a hand up or not. You can actually train that live using the camera feed on your computer using the JavaScript model because it's all working in the browser. So I would say that would be my first place to stop. And again, there's also plenty of examples on TensorFlow on how you actually go about converting, or rather exporting out a model in Python that you might have built in TensorFlow, or kind of doing a pipeline from scikit-learn through TensorFlow to output that. And then how do you turn around and simply call it? And that's what I did here. I just simply called it, and it's maybe 4 or 5 lines of code to just call it in and use it.
No more questions? I'd like to thank our 4 speakers for very